So looking at this problem here, we've got the powers of 2 sum through from 2 to the power of 0 through to 2 to the power of 2. So, and our general term would be 2 to the power of m minus 1, because when m was equal to 1, we got 2 to the power of 0. So we can look at it that way as well. That's equal to the sum of 2 to the power of m minus 1. So, like if you look at that, that's really, you can prove that using a geometric term. Like you can, that's the sum of a geometric series. But that's okay. You can prove it for yourself later on that that's right. But and you can see that how it's true by mathematical induction this way. So we sub in n is equal to 1. Gives us 2 power n minus 1 minus 1 is 1, and 2 to the power of 1 minus 1 gives us 1. It's true for the first term. It's true for n is equal to 1, which is nice. We assume it's true for n is equal to k, so we get our relationship here. We're assuming this statement is equal to this one. There's our assumption. Now, what we want to prove is that when it's equal to n is equal to k plus 1, that we get to the k power k plus 1 minus 1. A little bit harder manipulation, not too much harder, but a little. Just watch out for the tricks. We start with our left-hand side again. So when the k plus 1 terms, again, we know that sum is equal to 2 to the power of k minus 1. So we look at our k plus 1 term and collect our terms. The k plus 1, the k minus, the plus 1 minus 1 cancels. Leaves us with 2 to the power of k. Now if we have a look here, we collect our like terms. We get 2 lots of 2 to the power of k. We got our minus 1, which is what we want, but can this be manipulated to this one? Well, if we look and say, well, that's 2 to the power of 1, I'm multiplying there. What do I do when I've got the same base? I add my powers, so that would be k plus 1, which is what we wanted to prove. We wanted to prove that it come down to 2 lots of 2 to the power of k plus 1 minus 1. It's true. So there's our proof for that one. Just watch for those types of tricks. Again, Extension 1 Mathematics, Induction starts to get a little bit harder. We're starting to play around with our algebra in a little bit different way. So look for those subtle little tricks. It's not hard, but we haven't done much of that sort of thing, and haven't been required to do much of that sort of thing before. So we have to be aware of that's how we start to solve some of these algebraic problems. So in the question 5 here, we've got the sum of the negative terms. So negative 2, negative even terms will give us minus n outside of n plus 1 for n being greater than or equal to 1. So that's what we need to prove. Again, we'll start with n is equal to 1. Substitute n is equal to 1 there. Minus 2 times the 1 gives us that minus 2. We substitute 1 in there and put 1 in there. We get minus 1 times 2 gives us minus 2. True for n is equal to 1. We make our assumption as true for n is equal to k. So this statement is equal to this statement, and we want to use that later in step 3. So when we put n is equal to k plus 1, our statement's going to look like this: k plus minus k plus 1, and we put the k plus 1 in for n here, and add the 1. So we're looking to get a minus k plus 1, k plus 2 in there. So there's our required to prove in that statement. So I start at left-hand side. Start with what we're given. Our left-hand side, prove it's going to be equal to the right-hand side. So again, there's our sum of our first k terms from step 2. And so we make our substitution of the k minus k plus 1. That was our k plus 1 term, so we can expand that out. Minus 2k minus 2. Well, I did that. I possibly could have gone away with that. I probably could have left it as 2k plus 1 and then factorised it out. That's okay. If I do the expansion, don't get a cubic, which is not too bad. But if I expand it all out, I get a quadratic when I factor, and a nicer one when I factorise the negative out, which we need to do. K squared plus 3k plus 1 factorises the k plus 1, k plus 2. So it's proved it's true. Probably not the most elegant solution, but I still got there in the end without too much more work. Question 6. This one here is a sum of 5m plus 4, which looks like it's going to be an arithmetic progression. And it comes down to a general term, or general sum here of 5n squared plus 13n over 2. A little bit nastier. Does it work for n is equal to 1? we'll substitute 5 times 1 plus 4, which is our first term, 9, and gives us 5 lots of 1 squared plus 13, so 5 plus 13, it's 18 divided by 2, 9. It works for the first term. Does it? We assume it's true for n is equal to k, so that statement's equal to that one. So what we're looking to do when it's n is equal to k plus 1, put a k plus 1 in that spot there. So there's our required to prove. 5 lots of k plus 1 squared plus 13 lots of k plus 1. So here's where we're going to have to do some bit of manipulation and a bit of decomposition. So again, we start with our left hand side. So there's the sum of the first k terms, and then add the k plus 1th term, so we can make our substitution of the first k terms. We get the k squared, 5k squared plus 13k over 2 from step 2. Clean this one up and we got 5k plus 9. Now to get, I wanted all over 2 to end with, so I need a common denominator. So put it all over 2, that becomes 10k, that becomes 18. Now what I want to do, this is where our decomposition comes into play. We've got to get a little bit creative because I want 5 lots of k plus 1 all squared. And I want 13 lots of k plus 1. Can I decompose my numbers that I've got there? Like 5k squared plus 13k. Well, I don't really need that. I want the 13k by itself. I'll take the 10k and put it with the 5k squared. Then I've decomposed the 18 to be the 5 plus 13. Now if you have a look, that's allowed me to get into a nice form where I can factorize the 5 out that I want here. And I'm able to factorize the 13 out where I want here. To get the k squared plus 2k plus 1, gives me the 5 lots of k plus 1 all squared, and the 13 outside of the k plus 1, which is what we want there. And thus, down to our statement that we want to prove, is where, but look how we've decomposed it. Again, not a technique we've used too much. We've rearranged terms before, but we've really got to look and go, well, what do I need to manipulate down? I've kept in mind what I'm requiring to prove. So yeah, that's the key, is keeping that in mind so I know what I'm basically needing to do in this part here to break it down and just to get my factorizations and do my manipulations and decompositions of some terms. And the question 7 here is a little bit different. With the general term for this series is n times 2 to the power of n minus 1. Well, it's neither geometric nor arithmetic, but it comes down, we want to prove that it comes down to 1 plus n minus 1 times 2 to the power of n. So what if we've got that? Substituting 1 again, so 1 times 2 to the power of 0, which comes down to 1. 1 plus 1 minus 1 times 2 to the power of 1, well, that'd be 0, gives us the 1 there. It's true. We assume it's true for n is equal to k, so we can do our substitution. So when we do our required to prove, so we're substituting k plus 1 in there and k plus 1 in there. So k plus 1 minus the 1 would just leave us with a k outside of the 2 times k plus 1. So that's what we're aiming for. We get our sum of our first k terms there, and the k plus 1th term we've added on. So we make our substitution from that part. So that's what we had from step 2. Substitute that in. Now, again, a little bit of manipulation here. Again, keeping in mind, I want a 1 plus. So I've already got my 1 plus there. So I'm just going to keep that out the front and then play around with the rest of the terms here. So I've got k minus 1 times 2 to the power of k, and k plus 1 times 2 to the power of k. Now, I've probably done a little bit of, missed a step I could have played with here. So there's the 1 plus there. If I look at what I've got in common, I've got a 2 to the power of k. So if I took 2 to the power of k outside of that, I'd be left with k minus 1, and we'd had a k plus 1. And that's where the minus 1 and the plus 1 cancels and leaves me with 2 lots of k times the 2k. So if you're wondering how I went from that step down to that step, we've done that manipulation. We've just factorized the 2k, collected the terms there in terms of 2k, and we've got that. Now, again, I've played around, mucked around, I've changed it all around and went k times 2 to the power of 1, because I want 1 plus k times something. So I've got my k times 2 to the power of 1 times 2 to the power of k, and then because it's multiplying and the base is the same, I've added the powers, which gets me down to my statement that I want. So now I can make my step 4. So hopefully we're getting the idea of, okay, what manipulations we can do and need to do to solve some of these problems in terms of factorizing, in terms of our indices, in terms of when do we factorize, when we can expand. So it's not easy questions, and the more you do, the better you're going to get. But you've got to be able to get used to seeing a lot of those manipulations that need to be done to get down to our final answer. And keep remembering, you need to keep an eye on what you're required to prove every time, so you're making sure your algebraic manipulations are working towards that.